Hello Reactor enthusiasts. This is a tutorial video of the startup of an RBMK-1000 simulator. We are in the Chernobyl RBMK Reactor 3 unit, and if you watch my previous video of startup tutorial of this reactor, I did several mistakes in the readings of the steam and pressure of the drum and some other things that should not have been done. I realized after publishing the video, and I will repeat the video to do this correctly. In addition, in this video I will not talk about the cheat engine, installing the program, and I will not put music, so this will be a royalty-free video without ads from YouTube. And finally, the last difference will be that the turbine speed up will be done in the manual mode, not the auto mode, so this will speed up the overall process. I expect this video to be around maybe less than 1 hour, 15 minutes or so. Okay, so let's start. First of all, because the reactor level and hot well level are correct and stable, we can already start turning on the condenser circulating pumps, the two water treatment pumps, and also the associated valves. Condensate system, we turn on only one of the 3 pumps for the moment and set it into auto. The deaerator level set point is at 0. And we turn the 2 polishers. Okay, these 3 things are fine. Next, we need to start one of the 3 pumps of the Feedwater pumps and systems. And the procedure is, first we open the inlet valve. We see this opening. When it reaches 100%, we can start the pump corresponding to this inlet valve, and when the pump is on, we will open the discharge valve. So now we open the pump, and when this light's on, now we open the discharge valve. This will be the same procedure for the loop 1 and loop 2 pumps, and it is done in this way: first inlet valve, then pump, then discharge valve, to avoid cavitation. The drum level control is fine. It's in 1 element control, so the 3 element is not light up, and we are in the startup valve, auto setting, and level set point 0. Everything is fine. Okay, we can already stop the offline core cooling system. So we stop the pumps first, and then we close the outlet valve. We can let the inlet open. And this system, the one I just closed, the offline cooling control, is used to cool the reactor core after a shutdown. Because of the decay products of fission, will have heat produced many hours or days after the shutdown of a reactor. That's the reason why in Fukushima there was the accident, because of the heat produced after the shutdown, because the reactor was correctly shut down when there was the earthquake. And then, because this system, the offline cooling control, uses the grid energy coming from outside the power plant to run the pumps and keep cooling, if the grid is down, which was also the case in Japan in the Fukushima accident, then there is a a diesel generator unit that generates electricity to run these pumps. So this is the one we need to activate here and set it into auto. In case everything else fails, this will cool down the core. In Fukushima this also failed because the wave, the tsunami, broke the pipelines that were used to bring the diesel to the generators. Okay, so we can close these 2 already, and now we can go to the deaerator steam supply. Okay, so we set it into auto, so this will make the deaerator pressure be at this set point of 98.7, and we need to increase the deaerator vent valve to 50%. So I will increase now to, you need to keep clicking to increase this. So I will increase to 20, and then I will continue later to reach 50%. Okay, and I will leave just over the turbine diagram, so I will not forget before going to the turbine to do this. Okay, reactor drain control, this is to set the reactor level. We can set 4 inches here. Select this here and set it into auto. That's good. and then we will start the pumps in loop 1 and loop 2. It's the same procedure as the Feedwater pumps. So open one of the 3 pumps of each loop, wait for them to be at 100% of opening, and then turn on the pumps to avoid cavitation, and after that open the outlet. Okay, that's good. And now I will have a look into the plant overview schematic. And we see these 2 pumps here, which are the condenser circulating pumps are on. One of the 3 in the condensate is on. One Feedwater pump is on. One in each loop of the recirculation loops is on, and the water treatment pumps are on. So everything is good. We can already go to the turbine control. This is a turbine panel, and I like to put it here. To reset the turbine, because now it's in trip mode, we need to go into turbine support systems, and first of all start the lubricating oil. In a real plant, you will need to send an operator to check that everything is fine, there are no oil leaks and so on. If everything is fine, then you start the hydraulic lubricating system, and then open the steam drains here. We leave this stop for the moment, and once the turbine is in turning gear, we will start the steam seals. Okay, so now we go to the turbine, we reset. Now it's reset, and turn on the turning gear. We see the speed set point is increasing now. This number increasing here, 5, 6, 7. When it reaches 20, the turbine will be in turning gear. Now I can already open the alarm panel and put it here. Before I didn't do, because there are so many alarms I don't even want to read them. I click acknowledge, and these are the remaining alarms. So we see the message just appear, steam turbine now turning gear, because it reached 20 RPMs. So at this point we can start the steam seal. That's good, and we can already close this. At this point everything is ready to start the reactor. So we will start, because this is the RBMK design. This is a graphite moderated light water cooled reactor. This is a huge design. It's much bigger than the water pressure reactors used usually all over the world. So because this is much more tricky to control and don't incur in a critical runaway, we need to withdraw first only the central core rods, and that's why I will select here center core only, and then select fast, and then I will start withdrawing. But before starting touching rods, we need to do something. You see this warning here, warning reactor protection bypass. So now the auto scram is not activated. It means we could create a critical runaway and make the reactor explode. We need to connect the auto scram control here. Okay, now it's on. It means if now we do stupid thing, a scram will be triggered and the reactor will be shut down. Now we can start pulling rods. I click pull rods, and we see in the train chart here in the right top corner, the blue line, which is the neutron rate, starts increasing. We are in a source range now, it's not yet exponential. And we should be careful the neutron rate not to surpass 8%. If it surpasses 8%, we'll have an alarm, and if it goes further, we can have a scram. So let's keep looking at this neutron rate here. And meanwhile, I will go to the DA vent valve, which I left here before, and I will use this time to increase to 50%. Okay, 50%, and it's set into auto, so we can already close this window. Okay, neutron rate is at 4%. I will reduce the velocity maybe at 6% to medium and then to slow. And then we will need to switch to the full core withdrawal to activate Okay, we went to 8%. That was a bit dangerous, so we got... No, we didn't get the alarm. Okay, anyway, we should not surpass 8%. Okay, we're at 6%, and now I will click hold to avoid going above 8%. Okay, now I just click hold, and we see the trend going down. The neutron flag is still 0, and now we can already go to the automatic reactor control. So I switch it on, the automatic reactor control. I will just pull rods a bit more again. I hold it again, just to get a bit closer to a range in which we can operate automatically. And now I will reduce power set point to 1, because we're still at 0 at neutron flags. And then I will disconnect the central core, because if we have the center core only engaged, the automatic reactor control doesn't work. We need to use the full core. So we're at 1% neutron flags. I will increase to 1.5 here, and now I will pull rods. I will hold immediately after, because otherwise it goes to high the neutron rate. And now it's already controlled. I would say it's already in automatic control. I will increase here the power set point to see. Yes, now it went down because it was just a bit above the 2%. Now I can increase with automatic control to 5%, and we'll see how the neutron rate it goes up to accommodate this. Okay, 5.5%, it's fine. Now what we need to do is to wait for the drum pressure to rise enough to be able to connect the turbine. But another thing is needed. We need to go to the main steam dam control and increase the set point, because now it's at 1000, and it means if the pressure in the drum reaches 1000, the release valve will be opened. But if this happens before the condenser vacuum, which is indicated here in yellow, reaches the maximum vacuum pressure, this will create a disk rupture problem. We don't want this, because if this happens, we cannot continue with the simulation, and we need to, because we cannot connect the turbine, and we need to stop the simulation. So I will increase the set point to the value needed to connect the turbine, which is 7500. So I will just put the set point a bit above that. 8000 is fine. Okay, and set it into auto. This is already good. And now we're going to the aerator system supply. No, we already did this. To the condenser vacuum system. And we need to switch on the condenser air ejector. We see that even if we click, it doesn't light up, because it needs the pressure in the condenser vacuum to be high enough to activate. But we already click, so when the pressure is high enough, it will activate automatically. And the condenser vacuum breaker, it's closed, it's good. At this point, you can just wait for the reactor to create enough heat to boil water and create pressure. But because my purpose now is to do the fastest possible startup, I will increase power to 10% for the moment, and maybe even a bit further when water starts to boil. Okay. Now it's just a matter of waiting, and we already see here the pressure building up in the drum because the temperature just went above 100 degrees. The fuel temperature is 240 degrees now. That's totally fine. The maximum is around 1000, so we are very safe. The critical point of fuel temperature will be when we reach the power of the reactor about 50% more or less. When we are at this level, it's totally fine. Okay, and because the drum water is already boiling, I will increase a bit further the reactor power. But do not go above 15% because some systems need to be adapted for a power of higher than 50%. Like the Feedwater pumps need to have a second pump connected, also the loop 1 and loop 2 and several other things. So let's go to exactly 50 to speed up the process. Okay, and the pressure here is going up nicely, and at some point we will see how the condenser vacuum is created, and we see a yellow line here in the plot going up to the maximum. At that point, the main steam dam control valve could open without creating a disk rupture already. In this tutorial we will use the manual setting. It's here in the turbine speed control. So in the previous one, it doesn't matter if you didn't watch, I will tell you now what I did. I used the auto setting. So this setting, what it does, it cycles through these values of RPMs one by one at a constant speed. So you select either slow, medium or fast speed depending on the temperature at the beginning of the startup, and it ends up at 3600, and then you synchronize the turbine. This is quite slow, so now I want to try to do it manually and increase the rate of speeding up by opening more the valve control manually, and then we'll see how it works when we switch back to automatic at the end to keep the 3600 RPMs. We got to hide the radiator pressure. Let's see what's happening. Here we got a high pressure. This is normal when we are building up the condenser vacuum, which is happening now. If you look at the trend chart, this yellow line. So in a moment it will equalize. And you see the low condenser vacuum pressure warning disappeared, so this is good. The radiator pressure is still going up, but I think it will start going down in a while. You see it's already going down, 258, 257, so that's fine. It will equalize in a moment. Okay, next step will be when we reach 7500 here in the drum. We will connect the turbine and then manually action this valve at more or less 5% or even more to speed up the rotation of the turbine. But I know by experience that to keep the turbine at 3600 RPMs without synchronizing to the grid or without connecting to the generator, we need around 5% of opening of this valve. So this gives us already some information. When we are approaching this terminal value of speed, we will start closing the valve to have an asymptotic value of 5%. Okay, we have already many warnings disappearing. We have still low main steam temperature. I think this is a problem of the simulator. I think it means pressure, because I try to increase temperature in the main steam and this doesn't disappear. It disappears when it reaches a pressure of 7500. So that's my opinion. Okay, turbine is now turning gear. This is just information. The alarm color gives you information about if it's a warning, if it's information, or if it's a like, I don't know, critical thing. Okay, we're at 6000. We are very close to the pressure. We need to start turning a turbine. When we start turning rotating the turbine, we'll need to look a lot to this turbine status. This will give information about the vibration, differential expansion, temperatures of the rotor, stator, etc. And the pressure is already enough. Now we can start opening the valve. So you see by clicking the up arrow, the valve control signal is increasing. Now it's at 1%, and we don't see yet the turbine rotating. Okay, I need to click into open and then increase the valve, it seems. And we see the speed, it goes very fast to several hundred RPMs. Okay, that's very good. We're already at 1k RPMs, and you may see that vibration goes up a bit when we start and we are at several hundreds RPMs, but this is normal. Probably at these low RPMs we have a lot of resonant frequencies, and when we go above 1000, these resonant frequencies are left behind and the vibration is quite low. Now we can reduce the reactor power to 10% because the main steam dam control already opened the valve, so we are just waiting energy here. So 10% will be fine to speed up the turbine. I will open more the valve. Even if now increase speed very fast, you will see that this speed will slow down if you keep the valve open at the same amount during all the time, because the friction and the losses because of turbulence in the fluid increase with the speed of the turbine. So I will increase the valve opening to 12, let's say, and now we see it increasing very nicely. We see in the main steam dam control the valve is open at 11%. That's a totally fine value. It means we are just wasting 10% of the steam that comes from the reactor. That's a safe margin for not letting the pressure go below the set point that we need for the turbine, but at the same time not wasting too much energy. Okay, we're at 3000 RPMs. I will start to decrease a bit the opening of the valve to 11. I know I need 5% at the end, so I will increase. When I approach the nominal value of velocity, I will decrease it to the value I need. We're at 3000, almost 400. We're at 200 RPMs from the nominal value. Now I'm just above 5% by 1.5 points, and we're very close to the nominal value. Let's approach the speed we need slowly to avoid overshooting it. If we surpass 3600, we could break the turbine. So now we need to be very careful. Okay, I'm at 4.5 of opening, and we see this increasing very slowly. So when we reach 3600, I will select auto and let the auto setting to manage the velocity. Okay, we're almost there, and now I click auto. We see speed going down because the valve was closed at 3% at the moment of clicking auto, but now it will open the valve to go up to 3600, and at some moment it will stabilize these fluctuations, and yeah, now it's almost 5% of opening to go up. And now it's closing a bit to stabilize it, and you see now it's almost the nominal value. Okay, that went very smoothly. We are at 24 minutes of simulation, and we already connected. Didn't synchronize the turbine yet, but we are the turbine spinning at the nominal speed. Next thing to do is to increase pressure in the main steam dam control, because we cannot connect the generator with this pressure. The turbine would not have enough power to run the generator, and then it would draw energy from the grid, or it would create a trip directly. So I will increase power set point. Let's look at the valve opening. It should go to 0 or close to 0. Yes, it went to 0. So now I can just increase to the value I need, which is above 11,500. This is more or less the pressure needed by the turbine to be connected to the generator. So let's set it a bit above 12,000, so we don't need to waste steam by opening the waste valve. Okay, that's perfect. Now I will increase the reactor power to speed up the build-up of pressure. Not beyond 15%, for the same reason I mentioned before. Okay, I went beyond by 0.5%, but I just went back very quickly, so it's fine. We see the pressure building up, 9,500 already. And actually the normal procedure is to keep the reactor at 10% during this procedure, during this transition. I just did this to speed up a bit the process, but you are supposed to increase from 10 to 15% after synchronizing the turbine. So now I will go a bit lower once we approach the pressure we need in the turbine to do the synchronizing at the reactor power that actually it's supposed to. Okay, we're at 10% of reactor power again. The pressure set point in the turbine it's 11,000. At 11,500 we can already synchronize. Okay, so we are ready. For synchronizing we need to use this output here. This is the generator brake, and we need to break it when it's almost at synchrony. And we will use a oscilloscope to know when we are in synchrony. We are in synchrony when this arrow is in the top depth center here at 12. So if it's rotating in this sense, like clockwise, we'll need to close the brake just a bit before 12, like at 10 o'clock. And if it's counterclockwise, we will need to close the brake around 2 o'clock. But it also depends on the velocity it is rotating. So this is a bit tricky, and if we don't get the point well, we'll create a turbine trip. So I will close it now. And it went smoothly. The turbine is now connected. And we see generated load 3%. And now I will increase reactor power because of one reason. If the power from the main steam line is not enough to have a generated load higher than 0, because there is friction, there are turbulence in the flow, etc., it can happen that the generator draws electricity from the grid, and if this happens for this extended period of time, then a turbine trip will be triggered. So I increase power to 15%, and we see the generated load increase to 13, and we also see the main steam dam control increase to 10% the valve. It means we're wasting energy. We need to increase the set point a bit to avoid this. So 12,500 now. The valve is close to 0 now. The generated load is around 50. Okay, everything is smooth. Acknowledge these alarms here. And we can go to the next step, which is increasing power above 15%. For this, it's very important to do several things. We need to start the 3 Feedwater pumps. So I open the inlet valves of the pump number 2 and 3. When they are at 100%, I turn on the pumps. And then I open the discharge valves. Then we need to switch on the 3-element control. We leave this into auto, and we go into the main valve in the drum level control. The set point is fine at 0, and this is fine. Then for the turbine control valve select, we need to select main. We were in the startup for the startup procedure, So I select main, and you will see as main opens, startup is closing to keep the discharge what it should be. We also see now the reactor level and hot well a bit struggling to keep things on the good levels, but they will go eventually back to the good level. And finally, in the turbine support system, we need to close the drains. So we close the drain, that's perfect. And now we can increase power to 15%. I said 15 or what? It was 20. We increase power to 20%. Now we need to turn on the second condensate pump. That's on. And the second loop 1 and 2 pumps. We first open the inlet valve. We will not open the third one because we want a given amount of void in this reactor. This reactor has very particular characteristics, which is a positive void. Positive void means when we create void in the cooling water, which means boiling water, bubbles, so steam bubbles inside the cooling, this will have a positive effect on reactivity. So we want 2 pumps because 3 pumps will decrease a lot the void and will kill the reactivity. So 3 pumps are only used when needed, but at this moment we will turn on 2. We switch on the pumps and open the outlet valve. Okay. And we see the void percentage here, in this indicator here. If we have to try the 2 loops to have the same void, so we can adjust the flow with the trim, adjust to make the void in the 2 equal. Okay, the temperature in the fuel elements is fine. And what else? We can increase power to 25% now. Okay, that's very good. Things are going smoothly. Turbine set point is at 11.9 thousand and the drum is at 12,000. The set point for the main steam dump is at 12,500, so we have this 500 margin without opening the discharge valve. And now we can continue increasing power. To increase power further, we need to switch on the thermal power correction. At this point, the power set point will not control anymore the neutron flux. It will control the thermal power. This means that we could overshoot the neutron flux 100% value if we just look at the power set point. Now, from now on, we need to look at the neutron flux when we approach 100% of neutron flux to avoid overshooting it and creating a meltdown or a scram. Okay, so there is nothing else to do. From here to 100%, it's just increase power step by step, slowly, checking all the parameters while doing so. And we did this in 34 minutes. Let's see the total time that it takes us to bring this up to nominal power. I will go to 35 now, or 40, and then stop a moment. Okay. Also with the turbine, you saw we had no problem at all with vibration or differential expansion. That's also nice. So I didn't need to talk a lot about rotor temperatures and shell temperatures, but I was looking at them during the spin up, and the difference between the two was maximum of 20 or 30 degrees. And the differential expansion, which is plotted here, was always between these two red areas. The left one, which means the rotor is cooler than the shell, or the right one in which the rotor is warmer than the shell. And the vibration now is at 50%, not very low, but still fine. This is probably because of this. We have a bit of differential expansion even if we are not in the red line, and this creates some vibration. But anyway, we'll continue increasing power. We go to 50% now. Okay, now we will start to look at fuel temperature more carefully. 659, 654. The two void in loop 1 and loop 2 are equal, so we don't need to trim anything. Here the loop 1 and loop 2 recirculation pumps are like the core flow in a BWR reactor, more or less. So more flow means less void, but here the effect is contrary, because we are in a positive void reactor. If this was a boiling water reactor, more flow will mean more reactivity. Here more flow means less reactivity. Okay, everything is stable. I will increase the power. I will make a bigger step now. I will go to 65%. Okay. We see the reactor level decreasing. Let's keep an eye on that. And increasing back, so everything is fine. No worries whatsoever. Okay, let's increase power a bit further. Let's go to 80%. Oh, I went a bit too far. And now it's when we need to be very careful with the neutron flux, because even if we're at the power set point of 83%, we're at a neutron flux of 91%. We see a fluctuation in the reactor level again, and going back. Okay, now I will increase the power set point so I get a neutron flux of 95 more or less. Okay, we are almost at 95 neutron flux. And now we will approach the 100% of neutron flux very carefully, because if we overshoot it even by 1 point, well, I mean 0.1%, it will create a meltdown. So let's be very careful. We also have here void a bit higher in the loop 1 and loop 2, but I don't want to trim just for 1%. For the moment I will not touch it. Now it's equal, so it's fine. Okay, let's increase a bit further this power set point, so we go to 96% or 97.5, let's say. Perfect. And now we are at a generated load of 842 megawatt. In the previous video I just reached 415 because I did several mistakes. One is that I connected the three loops, the three pumps in the loop 1 and loop 2, and I'm not sure about what else I did wrong, but for sure now we have a higher generated load. I think this is the main reason, having the loop 1 and loop 2 with a too low void. Okay, I will increase the set point a bit more. So we go to 99 of neutron flux. Okay, 98.8, that's fine. I remind you, just to be safe, I will not approach to the last 0.1% to the nominal neutron flux, because I tried before, and if you reach 100%, even if you don't reach 100.1, it will create a meltdown. So maximum I will get here is 99.9% of neutron flux. Then getting thermal power, it's a matter of time, because we're waiting for fission products to build up and to release the heat in few hours of days after we restart this reactor. So we cannot get the thermal power up to 100% now, because this reactor doesn't allow us to get a neutron flux of above 100%. And we have a power of 856 megawatts. I will go half point higher. This will set us at 9. No, let's go 1 point. Let's go to 99. So there is 2 clicks. Yes, we are 99.1. I can still safely increase half point the power set point. So let's do it. We're at 99.6. I didn't expect this 6, I expected a 5. So now, unless the neutron flux doesn't go below 99, I will not increase again the power set point. And we see the generated load is at 874.5 megawatt. Now the turbine is behaving very well, low vibration. The differential temperature between the shell and the rotor, it's almost none, just 3 degrees. The rotor is at a bit higher temperature, vibration at 8%, and it seems it's decreasing. We have a neutron flux of 99.3. It means if I increase half point now, we should go to 99.8. I could do it now, but I feel a bit nervous. I really don't want to end up with a scrum, so I will wait a bit. We also see the main steam dam control is still at 0 opening. Set point, it's above the value, but I will just increase the set point just to be safe, so we don't waste any energy. This is the maximum, 13,500. And now I will increase the power set point, half point, and we go to 99.7. Thermal power 94.6. So we still have a lot of room to go to 100% thermal power. And I think at the rate this neutron flux is decreasing according to the increase of neutral power, now it will take a long time to go like at 99.2. So probably it's a good point to end the video. It took less than 45 minutes now, it's 44 minutes to reach 878 megawatt. I will write this down. 45 minutes, 878 megawatt. And this is the correct setting. The loop 1 and loop 2 needs to have 2 pumps each, not 3. We see the void almost equal. Maybe we'll trim a bit the void of the loop 1. Just decrease. Oh, okay, it's the contrary. I should decrease flow in the loop number 2 to increase a bit the void. And we see here loop number 2, it's at the temperature 10 degrees below the loop number 1, the fuel. So let's trim. Okay, now it's at 18, so I will stop trimming. I trim until 26%, and hopefully if we wait some time the fuel in the loop 2 should heat up to this value. Neutron flux at 99.4 now. Too dangerous to increase that point, I will not do it. And power still at 878. We see indicated in red the hottest fuel assemblies in the reactor. And all the other systems are fine. The turbine is spinning at 3600 RPMs. And now we are at 99.3. We could still increase half point without overshooting 100. What do you say? Do it or not? Okay, let's do it. We should not pass 99.9, so okay. Oof, my heart almost stopped these 3 seconds. Okay, we're at 99.9, but I assure you, if we reach 100, we have a meltdown. We don't need to surpass 100. I have experience on this. So, generated load 885, thermal power 94.9. So I will do a small calculation to see what's the theoretical maximum load. $886.2 divided by 0.949. Okay, so if this is linear, and it should more or less be linear, if we have a thermal power of 100%, we should have 933 megawatts in the generated load here. So these are called RBMK-1000, but 1000 is approximated. In this simulated sims we could reach 933. Okay, I will stop the video here. It's below 50 minutes. I think we did a good job bringing this up to power in less than 1 hour. I thought this was much more complicated than the VVER-1000, and this is what I said in the previous video, but after several simulations I feel that if you really know what you are doing, this could be not more difficult than the VVER. Even it could be a bit easier because it has the automatic control for the power, and you can pull rod just clicking. You don't need to keep press the button, and overall it's quite, I would not say intuitive, because you really need to know what are all these things for and know the procedures, but the physical neutronics of the reactor don't bring too many problems, and the turbine can be connected also without too many problems, no vibrations, and everything was fine and smooth. Okay, I hope you enjoyed this, and see you soon. Bye.